In section 8.4, we're going to be working with an integration technique called Trigonometric Substitution. The book gives you three summary substitutions to make. The first one is if we have something of the form a squared minus x squared. Now I'd like you to remember that this only works for root a squared minus x squared by the looks of this particular formula from the text, but this actually works for anything of the form a squared minus x squared. It could be to the 3/2, which of course with the 3/2 we have a square root. It could also be a squared minus x squared to the squared, which is the same as a squared minus x squared to the 4/2. So this works for other things other than just a square root. And I want you to keep that in mind for all three of these. It kind of looks like it only should show up underneath a radical, but it can show up in other ways as well. Now the idea behind this is when we see certain values in our integrand, we should be able to make a substitution. So if we see something of the form a squared minus u squared somewhere inside the integrand, we should let u equal a sine theta. If we see something like a squared plus u squared somewhere in my integrand, I could try and integrate it by letting u equal a tangent theta. Now these don't seem very intuitive, but if you think about the derivatives of your trig functions, these will make sense. If I have the integral of 1 over a squared plus u squared, that integrates into 1 over a inverse tangent u over a. So if you review those integrals, that will be a little bit helpful in recalling what's going on with these. If we have something of the form u squared minus a squared, then I would let the substitution u equal a secant theta work. Now these formulas up above from the text, it's the same thing, just a little bit shorter notation. So you need to know these when I use what type of substitution. Some other things that are going to be handy to know are the Pythagorean identities. Most of us have this first one memorized, sine squared plus cosine squared equals 1, but we also need to know the other Pythagorean identities of 1 plus tangent squared equals secant squared, and 1 plus cotangent squared is equal to cosecant squared. These are usually a little bit easier to remember if you recall that sines go with cosines in terms of derivatives and integrals. Tangents go with secants. You know, the derivative of tangent is secant squared, and the derivative of cotangent is a negative cosecant squared. And I'm not saying that those are a direct relationship, but it's one of the things that helps you remember these. And you definitely need to have these memorized as well. There's a few other trig identities that will be helpful as well when you're working with trig substitution. These other trig identities we've also looked at when we were looking at trigonometric integrals, your half angle formulas right here, and also this nice little identity that takes a double angle into two single angles. So these are definitely ones that you'll want to know as well. So we would want to memorize these as well. And they're going to come in handy when we start working problems. So the integral that we're going to look at is 1 over 4 plus x squared dx. Now one temptation might be to let u equal the 4 plus x squared. Du then would be 2x dx, which I don't have. So u substitution won't work here. Calc 1 methods won't work here. So let's go ahead and try trig sub. Now with trig sub, what I need to do is identify what type this is. Is this an a squared plus u squared, a squared minus squared, or u squared minus a squared? Well, this definitely looks like an a squared plus u squared. A is some constant, u is some function of x, so that's definitely what I have here. So in this case, a is equal to 2, u is equal to x, and the recommendation for the substitution here is to let u equal a tan theta, and that comes from right up here where I have an a squared plus u squared, and I should let u equal a tan theta. So down here, let's go ahead and complete that substitution. U in this case was x, a is 2, so I get x equal 2 tangent theta. Now I also have to find dx. The derivative of tangent is secant squared of theta d theta. Now one thing I want to keep in mind, the name of this process is called trig substitution. So now I need to make that substitution. Well, in place of the 4, I'm not going to do anything. In place of the x, from over here, I put 2 tan theta, and of course that's going to be quantity squared. One of the most common mistakes is for everyone to forget to plug in for this dx. Plugging in for dx, I have 2 secant squared theta d theta. Now it's our hope that what we have here is actually easier to integrate than my original, and it actually looks quite a bit worse, but we can simplify this. So let's go ahead and simplify this a few steps. First of all, I have 2 secant squared theta d theta in my numerator. In my denominator, I'm going to have 4 plus 4 tangent squared theta. Now right away I see that I can factor out this 2 from the numerator, I can factor out a 4 from the denominator, and that will simplify things just a bit. And so for my denominator, I'm left with 1 plus tangent squared. But from up above, we know that 1 plus tangent squared is going to be equal to secant squared. So when I make that substitution, I end up with 1/2 secant squared over secant squared, which is just going to be 1 d theta. So the algebra in between with the trig is a little bit difficult, but I do get this boiled down to a nice integrand. So what is the integral of 1 d theta? Well, we have to look for that theta value to indicate what's our variable of interest. And what I end up with here is 1/2 theta. And you might say, okay, that's my solution. But it isn't. My original was in terms of x, and so should my solution be. So now I need to convert back to x. Now this is kind of one of the trickier parts of this process. And you don't have to do this with every problem, but for this one we need to, because I have theta here. Well, what is theta? Well, if you look up here, theta is some angle. So what we're going to do is we're going to use a triangle to help us convert back. Of course, right triangles are the easiest ones to use here. I started with x equal 2 tangent theta. That was my original substitution. If I solve for tangent theta here, I get tangent theta equals x over 2. Well, using your SOHCAHTOA for a right triangle, this is equal to your opposite leg over your adjacent leg. So what I need to do is mark some angle in this triangle as theta, and I need to mark tangent then. Tangent is opposite over adjacent. Using the Pythagorean theorem, then, I get that the hypotenuse, which is always opposite the right angle, is equal to the square root of 4 plus x squared. Now that's going to help me solve this, because now I can plug in and say, okay, I had 1/2 theta here. Well, what is theta? And the answer to that is I don't know. I have no idea. But I can come up with it by using an inverse trig function. So I could say, okay, well, theta is the angle that has a particular sign. So I could look at this in terms of 1/2, and let's use tangent here, just because I have tangent that I'm already working with over here. 1/2 inverse tangent of x over 2 plus c would be a solution. Now remember, this right here, this value right here, means what angle has a tangent of x over 2. And from looking at the triangle, you'd say, oh, that's easy enough. That's theta has a tangent of x over 2. So that would be a solution. There's other solutions here as well. I could have 1/2 inverse sine. Remember, sine is opposite over hypotenuse. X over root 4 plus x squared plus c. That would be a solution. I could also have an inverse cosine. Cosine, if you recall, is adjacent over hypotenuse. And these are all correct solutions. None of these are incorrect at all. So if you check your answers in Maple, sometimes you're going to get something that doesn't quite match up with what you'd think, but these are all correct solutions. I could also use inverse secant, etc., but of course those get a little bit more complicated.